Welcome to Public Health on Call, a podcast from the Johns Hopkins Bloomberg School of Public Health, where we bring evidence, experience, and perspective to make sense of today's leading health challenges. If you have questions or ideas for us, please send an email to publichealthquestion@jhu.edu. That's publichealthquestion@jhu.edu for future podcast episodes.
This is Lindsay Smith-Rogers, producer of Public Health on Call, and today we start a series of podcasts that we're calling Vaccines 101, the basics of vaccines and vaccination from the molecular level to global policy and everything in between. We start with the biology. Dr. Arturo Casadevall is the chair of the Department of Molecular Microbiology and Immunology at the Johns Hopkins Bloomberg School of Public Health. He speaks to Dr. Josh Sharfstein about what vaccines are and how they work. They also discuss new developments in vaccine science. Let's listen.
Arturo Casadevall, thank you so much for joining me today on Public Health on Call to talk about vaccines. How are you doing?
I'm doing fine. Thank you, Josh, for having me.
Given this topic, I wonder if you could introduce yourself again to our listeners. You've been on a few times, but I don't know that people necessarily appreciate your role and your training.
I'm professor and chair of the Department of Molecular Microbiology and Immunology. I am an infectious disease physician. I have a PhD in physical chemistry that helps me think about vaccines. But I think for the purposes of this podcast, I should say that I've been working on vaccines for 30 years.
Great. Now, at the highest level, how would you describe a vaccine?
At the highest possible level, Josh, I would say that they are humanity's greatest invention. But let's just talk about what is a vaccine. It's been known since antiquity that when individuals got an infectious disease and recovered, they were immune for the rest of their lives. And that observation meant that the body could learn from the experience to then protect itself against future encounters with the same microbe. So what vaccines do is they teach the body to protect themselves against a specific microbe without taking the risk of an infection.
In other words, you could get immune by getting the disease, but if the disease kills you, that's not a great bargain. If you get a vaccine, then you can become immune without having to go through the disease in the first place.
Exactly.
Now, within the body, how does that actually work? Tell me a little bit about the immune system. I noticed you're chair of the Department of Molecular Microbiology and Immunology. That's the immune system. So how does the immune system address vaccines?
So when you think about the immune system, it's important to think that you have this wonderful layered system of defenses. And when it comes to vaccines, there are two major defenses that are activated. One of them is antibodies. What are antibodies? They are proteins, they are molecules, and they are in the liquid phase of the blood. And then you have something called cell-mediated immunity. And those are cells, and they tend to be something called T lymphocytes. They tend to be NK cells. And these then both coordinate the immune response as well as provide backup when one has to clear a virus or a bacteria.
So it is by interacting with the body, vaccines create a reaction both from antibodies and from cell immunity. Is that right?
Correct. You almost always get them both. From a regulatory point of view, that you often measure antibody because antibody is the easiest thing to measure. So if you can correlate that Josh has so much antibody, and this is associated with protection, then one can basically know how effective a vaccine is in a population.
Take me for a second into the body. Let's say we have an extremely tiny camera, and we were following the injection of the vaccine into the body. What would happen at the cellular level?
Oh, at the cellular level, let's just put it, you went to the doctor, you got a shot in the shoulder. The vaccine, first of all, it's in the liquid that the doctor gives you. And it goes through small channels into these small organs that we have called lymph nodes. They are part of the immune system. And right there, the immune system is able to break down the vaccine and to learn from it, the components. So the way to think about it is that the shot is a set of instructions to make both antibody and cell-mediated immunity such that if you ever run into the microbe, you can defend against it.
So what is in that shot? There are different kinds of vaccines. Could you explain that classification?
So when you hear vaccines, we have dozens, and they are very different. They range from a kill microbe. You can take a microbe, you can kill it, and just give it as a vaccine. You can take a microbe or a virus and attenuate it. And then it no longer causes disease. It's lost virulence. But the body sees it and deals with it and learns from it just as it was the wild virus. And you can take a piece of a bacteria or a virus and then prepare it in a way to become a vaccine. The vaccines generally have what I will say the instructions, which is what we call the antigen to make an immune response. And then they have other things like stabilizers, things to make sure that bacteria don't grow on it. They tend to be relatively simple formulations.
Sometimes they have chemicals to help the immune system respond, to stimulate.
Exactly. Sometimes they have what are known as adjuvants. And these, what they do is, an adjuvant is almost like giving a booster. It basically just increases the response to the vaccine.
How do the mRNA vaccines work? It's a little bit different because you're not actually getting a piece of the virus.
Very different. And I just want to say I have gotten at least 8 shots. And I think that they are a remarkable invention. And they are responsible for saving millions of lives. So the mRNA, what happens is a virus is composed of protein and it's composed of what we call nucleic acids. They can be like DNA and RNA. But what you're doing here is the pharmaceutical industry has made the instruction book only, which is the mRNA. So that goes into the shoulder, again, but instead of going into the lymph nodes, it goes into the muscle. And then when it goes into the muscles essentially read the instructions. They make the protein of the virus, and then you basically have produced in place the protein of the virus that then the immune system recognizes and then basically provides an immune response. And that's why your arm is often sore, because the proteins are being made locally, and the immune system is responding to it. And you feel it by saying, oh, a little bit of inflammation. Oh, my God, my arm is dead. And by the way, it lasts a couple of days, and then you're protected.
So to be clear, there are some vaccines which are the virus that is killed. Some, the virus is alive but very weak, can't really cause disease. Some, you're taking a piece of the virus. And then the mRNA, you're giving the instructions for the body to make a piece of the virus.
Exactly. It's amazing.
And then the net result is the immune system reacts to it, and you're protected as if, in a way, you had actually gotten sick in the first place.
Correct.
Now, there are some viruses that are very susceptible to vaccines. Like, there's certain vaccines that are just amazingly effective. And there's some viruses, notably HIV, where people have been trying to make a vaccine for decades. Why is it that there's some conditions, some disorders, some pathogens that can be fought with a vaccine, but others, it's been so hard?
The major mechanism is that making vaccines difficult is if the virus has the capacity to change very rapidly. In that case, the immune system cannot keep up with the changes. And that's what happens with HIV, and that's what happens why we can't clear the infection once we get it. So the problem with HIV is, imagine the immune system is a cop, and basically say, go after the person with the red coat. And by the time they get there, they have changed their coat to green, and then to blue, and then to brown. You simply can't keep up. But I would say that progress continues to be made. And I'm confident that eventually one will find a vulnerability in this system that can be targeted by the immune system, and that then one day we could have a vaccine to eradicate this terrible virus. Another very difficult virus to make a vaccine to was respiratory syncytial virus, that was discovered, by the way, in our department in 1957. And in the 1960s, they tried to make a vaccine that was kill virus vaccine, and it just did not elicit a protective immune response. In fact, people got often sicker than they would not have otherwise. But then came molecular biology and structural biology, and people were able to solve what was the key to how the cell would see a virus. And they were able to make a new vaccine that was licensed last year. And it's a phenomenal vaccine, and it's a testament to human ingenuity.
There are some vaccines that produce an immune response to a number of different proteins. And when that happens, sometimes there are certain proteins that are the most important for protecting someone compared to other protein responses, maybe not so important. Could you talk about how you think about stimulating the right kind of immune response and versus an immune response that maybe doesn't really matter that much for protection?
Right. So let's take COVID. So COVID is a virus. So when you get an infection with COVID, you mount an antibody response and a cell-mediated response to all the pieces of the virus. But the only one that matters for protection is going to be what they call the spike protein, which is this protein that sticks out, and they call it spike. So you don't need all the other proteins to make a vaccine. That is why the mRNA COVID vaccines teach the virus, basically give you mRNA, and the only protein that is made is the spike protein. So yes, not all viral proteins are of equal importance. And scientists work very hard to try to identify what we call what is the key protein that elicits protective immunity. And once you have that, that's often the first step toward making a successful vaccine.
You also have the advantage that you don't have to give the whole set of proteins to somebody, and that may be safer than getting the virus itself. In terms of the biology of vaccines, are there any misconceptions that you've noticed that you would like to take this opportunity to correct?
There are a lot of misconceptions, and I think the people, look, I work on this. This stuff is hard. Even I have to look things up. So I think that it's not surprising that the general population may not have a full understanding how vaccines work. But the one thing I would say is that the vaccines that are available are incredibly safe. They've all been tested. They don't cause autism. They save lives. I will give you one anecdote, Josh, from my life. When I trained as an infectious disease doctor, even though I'm an adult ID doc, we used to cover pediatrics. And I was at the Bronx. And every week we would have a baby or a young child with Haemophilus type B. 1/3 of those children died. 1/3 of those children had developmental problems as a result of having a meningitis. And 1/3 recovered without any problems. A vaccine was introduced in the early 90s, and I never saw another case again.
Yeah. Well, I trained in pediatrics starting in 1996. And how many cases of severe Haemophilus influenza type B disease did I see? None.
Well, I used to see one a week in the Bronx, covering Jacobi Hospital and Montefiore Hospital. And it was horrible. I mean, these were well babies, well kids who basically would develop meningitis and life-changing events from death to being left. Think about it. That doesn't happen anymore.
Yeah. And to put this in the context of our discussion, the reason that this disease is gone is that all babies now get this vaccine, which has a piece of the bacteria in it. It teaches the immune system of the babies to recognize this bacteria and kill it before the babies get sick. And as a result, this really effective vaccine has wiped out this disease in the United States.
Absolutely. And I would say, Josh, that conjugate vaccines are another miracle of modern medicine. We have them against pneumococcus, and we have them against meningococcus, the cause of meningitis in young adults. And they are essentially, in vaccinated individuals, you don't see the disease. And these are life-threatening diseases of high consequence, even if you survive them. They are truly modern miracles.
Well, Dr. Arturo Casadevall, thank you so much for joining me to talk about the science of vaccines, and really appreciate it.
Thank you, Josh.
Public Health on Call is a podcast from the Johns Hopkins Bloomberg School of Public Health, produced by Joshua Sharfstein, Lindsay Smith-Rogers, Stephanie Desmond, and Grace Fernandez-Cesiri. Audio production by J.B. Arbogast, Michael Bonfils, Spencer Greer, Matthew Martin, and Philip Porter, with support from Chip Hickey. Distribution by Nick Moran. Production coordination by Catherine Ricardo. Social media run by Grace Fernandez-Cesiri. Analytics by Elisa Rosen. If you have questions or ideas for us, please send an email to publichealthquestion@jhu.edu. That's publichealthquestion@jhu.edu for future podcast episodes. Thank you for listening.